In this next section, 13.2, we wish to discuss density and specific gravity. Now, although this is a section describing fluids, the discussion of specific gravity and density applies equally and certainly to matter that is solid. So first of all, let's describe what we mean by mass density. The first thing you would say is, well, you're talking about mass density. Is there any other kind of density? Yes, we can have density of charge, electrical charge, or density of other types of things. But really, in general, when we use the word density, we mean how much of that we have per unit volume, and sometimes per unit area and per unit length. Here we're discussing mass density. So this is going to be mass per unit volume. And we define our density as with the symbol rho, which is almost always used as a descriptor of density. And again, that's why we need to be familiar with the Greek alphabet to know that this is not a P, but a rho, letter of the Greek alphabet. And rho is the mass that we have divided by the volume that it occupies. The units of this are going to be kilogram per meter cubed. And there's no particular name for this unit. It's just kilogram per cubic meter. And as you know, we have at the beginning of the course described something that defined the kilogram, namely the density of water. The density of water is equal to 1,000 kilograms for every cubic meter. Or if I have a tenth of a meter by a tenth of a meter by a tenth of a meter, then of course I'm going to be dividing this by 1,000, and that defines 1 kilogram. So 1,000th of a cubic meter of water weighs exactly 1 kilogram. So this is a very important concept because we define mass based upon this density. Here are some other densities you may want to look at. You see water here is 1,000, and brass is 8,470. In other words, 8.5 times as much as water. Gold is 19,300, so it's much, much heavier. 19 times as heavy as water by an equal volume. Lead is 11 times, or 11.3, and mercury is 13.6. Kind of an interesting number to remember because mercury is a very unusual liquid, being a liquid at room temperature, whereas most substances like metals are never liquid except at very, very high temperatures. Mercury is a liquid at ordinary room temperature, and therefore is used in things like thermometers and so forth. You can see from this that since mercury is so very dense, you could actually float lead on it or float brass on top of a pool of mercury, and it would be suspended, and of course water. If we look at some other densities, wood is 550. And you'll notice, therefore, that since wood is 550, it's about half the density of water. Now, common sense would tell you then that about half of a piece of wood would stick out of the water, the other half would be submerged. This is a very interesting density, ice. And ice has a density of 917, which is less than the density of water, therefore ice floats. If ice did not float, we could have some real problems with our oceans, referring here, of course, to salt water and salt ice. But nevertheless, if ice were more dense, the ice would sink to the bottom. Since it's very, very cold down there without much sun, the oceans could begin to freeze from the bottom, and that would be a real catastrophe. With a tremendous amount of ice submerged, a large part of the oceans would have huge glaciers down underneath. Instead, this ice, whether it's freshwater or saltwater ice, floats on the water. And you can see the old saying that 90% of a glacier is underwater. Sure enough, here we have 9/10 or 90% of it would stay beneath the water and 10% would stay above. Aluminum, very, very lightweight compared to something like brass, which is 8,000. Aluminum is only 2,000, or let's say rounded to 3,000. Now looking at some gases, if we look at gases like air, helium, hydrogen, and oxygen, you'll notice that air and oxygen just as well are about 1.29. So the density of air is about 1.29, and that would be kilograms per cubic meter. So water, being 1,000, is about 1,000 times as dense as air is. But air does have a mass. It weighs a kilogram for a cubic meter. And that's not something you can easily see, because if you take a cubic meter of air, it's not obvious that this is going to weigh essentially a kilogram. That's 2.2 pounds, but it does. Water, of course, would weigh nearly a ton, 1,000 times as much. Helium is much, much lighter than air, 0.18, almost 1/10. Therefore, balloons with helium, and certainly with hydrogen, which is half of the density of helium, both of those are much, much lighter, and therefore things like balloons with helium or hydrogen will float. Oxygen is very close to what air is. Of course, air is made up of about 20% oxygen. Let's next turn our attention to specific gravity. The specific gravity is a dimensionless quantity, meaning that it has no dimensions whatsoever. And that's because it's the ratio of two things that do have units. It's the density of a substance divided by the density of water. And so if we have a density of let's say if we look at gold, that would be 19,300. If we divide that by the density of water, 1,000, we get 19.3. So we would say the density of gold is equal to about 19.3, whereas lead is 11.3. And of course, air is something like 1/1000th, so it is very, very small. The specific gravity of water is equal to 1, because it's the density of water divided by the density of water, and this has no units. It doesn't matter whether you're using pounds per cubic foot or whatever, as long as you're using the same pounds. When you divide the density of the substance by the density of water, those units are going to cancel and you end up with a dimensionless quantity. And that's why it's very useful. Now let's talk about the specific gravity of a human being. If we think of a human, you may have heard the expression that a human being is about 90% water. Well, there are two other things that are main components in a person other than water. Generally, you have fat, which is a lighter weight than, less dense than water is. It would float. And you have bone, which would sink because it's of a greater density. And if you have a nominal amount of fat on your body, if you're very lean and in good condition, then in fact the fat will not quite support your bone, and you will have a density slightly greater than 1. When you do, if you let the air out of your lungs and relax, you'll begin to sink in a swimming pool. This is kind of a good measure of how fit you are and whether or not you have excess fat. It's much more difficult for women to sink than it is for men, because women naturally have slightly more larger concentration of fat per mass of their body than men do. So it takes a woman who's extremely athletic and very lean in order to sink in the water. Perhaps a cyclist or a gymnast who has very little. A man should really try to achieve a state where he will sink when he's in water, and therefore has a lower body fat content. So, in general, we can approximate the density of a human by a specific gravity of 1. And so it's very neat that you can then take, if you know the mass of a person in kilograms, we can then figure out what their volume is by simply multiplying by the density of water. And so a problem that you might consider then is, let's take a 100 kilogram man, which is 220 pounds, and if we divide that by the volume of that person that we want to compute, if we say that, well, that density is going to be the same as water, it's going to be 1,000. So what would we expect to be the volume of a human being? They have 100, this is a 220 pound football player, and they just exactly neither float nor sink, so they have the same density as water. So their mass, 100 kilograms divided by their volume in cubic meters, is going to be equal to 1,000, which is the density of water. So I can solve this for V, taking the V over here, taking the 1,000 here, and we see that such a volume is going to be 100 divided by 1,000, or the volume of a human is something of the order of 1/10 of a cubic meter. Very interesting fact. And of course, each person is different. If you take a woman who weighs 110 pounds, she's only going to be 50. She's only going to be 50 kilograms, and therefore you'd have half the volume of this. We'll be using mass density, and like other equations, where this is the definition right here, given two of these terms, we often will require that we know the third. You certainly are required to remember that the density of water is given by 1,000 kilograms per cubic meter. And usually on the tests or exams, you will be given other types of densities, but you should remember that gold is the most dense. And Archimedes used that to, in fact, be able to derive whether or not any crown had been tainted with non-gold or was impure by looking at the density of the crown, as we'll talk about in just a moment.